Right. Hello, everybody. So I'm Avishai Tal. You've met me in the previous lectures, but now this is the first lecture that I will be presenting. So we're going to move to a new topic. We're going to start talking about graph algorithms. And today we're going to talk about decomposition of graphs. Some of these topics might seem familiar to you. Maybe you've seen them in 61B. But we will enhance them with a lot of new algorithms that you probably have not seen, and also more rigorous viewpoint and perspective. And we will actually prove that these algorithms are doing what they're supposed to do, and we do it in a rigorous way. Okay, so maybe before starting to talk about graphs, maybe let's talk a little bit about motivation. Why do we care about graphs? Why do we want to apply algorithms on graphs? Well,
is it okay if I interrupt for a second just to make the announcement about Piazza? Sorry.
Yes.
A quick announcement in case you aren't looking at the chat. We are moving the chat discussion to a live Piazza thread, which I will paste in the chat. It's also pinned on Piazza. And that way it's easier to consolidate the answers to questions instead of having everything fly by in the chat. So just go over there first. Thank you.
Yeah, and I'm very happy to see that there's like a lot of questions during the meeting. So feel free to ask these questions, and also to, when relevant, feel free to unmute yourself and ask the question. And I hope that we would have a very lively discussion as we had in the previous weeks. Okay, so I was starting to say that graphs are like a very important model, and we can model a lot of real life data using graphs. So some well-known examples is that we can write the graph of all the roads. We can look at the graph of a social network. We can look at the internet as a graph. We can think of the brain as a graph, where each node is a synapse. And there are numerous examples of real life models that we can model using this more abstract notion of a graph. Now, how do we abstract graphs? We care about two objects, right? We care about a set of vertices and a set of edges, which correspond to pairwise relations between vertices. Edge set. And the edge set, it's going to be just a subset of all possible pairs. So for example, we can have like UV can be an edge if U and V are both vertices, right? So this is should be very familiar to you. We are talking about algorithms, so we will need to say everything with respect to the length of the input. So here we would have two parameters that we would care about. One is the number of vertices, which we usually denote by N, and the number of edges that we usually denote by M. Okay. So when we talk about graphs, there are two types of graphs that we are going to be concerned with, and one is the directed version, and the other is the undirected version of a graph. Right. So we have the undirected and the directed. In the undirected case, these pairs don't have a direction, meaning that if UV is an edge, also VU will be an edge. And if you want to say it differently, you can just say that the edges are not ordered pairs, but they are unordered pairs. In the directed case, this is not necessarily the case. So we could have an edge from U to V, but not necessarily an edge from V to U. And we can think of it, this is something that can come up in real life. So for example, if we want to model, let's say, roads, some roads are one way. Or maybe some roads are two way, but there's like a different cost to each direction. Maybe you need to pay some fee to go in one direction, and you don't need to pay a fee on the other. So, and we will see that, the difference between undirected and directed graphs, sometimes in the undirected case, the algorithms will be much simpler. And also the notions would be much simpler. In the directed case, we need to work a little bit harder. Okay. So just, I'm sort of like doing these things that you've probably seen before, but I want to do it so that we would have like a common language so that we can continue to discuss more sophisticated ideas based on a common language, okay? So when we talk about graphs, we need to represent them some way in our computers, right? So we need to think of, data structures for them. And there are two, well-studied and widely used data structures. So one is an adjacency matrix. So we can have an adjacency matrix. So I just write an n by n matrix where each row corresponds to a specific vertex and each column also corresponds to a specific vertex. And I put, on the ij, so this, let's call this matrix A. So I put aij equals 1 if and only if, let's say, the ith vertex and the jth vertex are connected, meaning that there's an edge from the ith vertex to the jth vertex. Okay, so I'll put a 1 here. If it's not the case, I'll put a 0. Okay, so this is one way to represent a graph. The other is to represent it using an adjacency list, which is just to say for every vertex, let's say for vertex 1, I specify which are the neighbors of this vertex. So let's say this is 3, 7, and 10. For vertex 2, it's, I don't know, 3, 4, and 8. And for vertex 3, it's 1, 2, and 9, and so on and so forth. So here, for example, I chose a symmetric, undirected graph. You see that there's an edge between 1 and 3, and also between 3 and 1, and also between 2 and 3. So just a quick question, just to make sure that we are on the same page. So how would the adjacency matrix of an undirected graph would look like? Right. So I see that in the chat, you're saying, right, the matrix will be symmetric, meaning aij will be equal to aji. And this is exactly the definition of undirected. The edge exists between u and v if and only if it exists between v. Okay, so far, this is just a recap. Right, so we said that we have these two data structures or representation of graphs, the adjacency list and adjacency matrix. Let's talk about, which one should we pick? How should we represent the input? So I listed here like 3 operations, and I want to show the trade-off between these two representation. So if we just need to check whether an edge is in, whether a pair UV is an edge or not, then in the matrix form, I can do it very easily, right? I just go into the relevant entry in the matrix. So this would take O of 1. In the list case, right, if I have an adjacency list, if I want to check, for example, here in the previous thing, if I want to check whether 1 and 10 are connected, then I need to go over the list of 1 and go over it one by one until I see whether 10 appears there or not, right? So how much time will it take in the worst case to check whether an edge exists if I have an adjacency list? It would take time linear in n, so order n. But let's be a little bit more precise. So it will take, the time it will take is the length of the list, right? So if the list has 3 elements, it will take us 3 time steps. In the worst case, it will be n, but to be more precise, it would be the degree of the vertex u, right? So I'm looking at the vertex u and I'm looking at all its neighbors. It has du many neighbors. So this will be the time that it will take me. How much time will it take me to list all the neighbors of u? Well, in some sense, we already have a list of it. So you could say that it's order 1, but if I just want to output it, then I can just iterate over this list and it will take again order the degree of u. on the other hand, in the matrix form, even if I have, two neighbors out of, 1 million vertices, I still need to go over the entire row and find all these, which entries are 1 and which entries are 0. So it would take me order n, and I cannot do it faster in this representation. What about the space complexity? The matrix is really n squared entries, so there's not a lot to say about that. And if we look at the adjacency lists, so I have an entry for every edge, and I have a list for every vertex. So the total space complexity is order n plus m. Recall that n equals the number of vertices and m equals the number of edges. Okay, and actually, when I thought about it, you could probably also think of, data structures that have the best of both worlds. But for us, we would usually look at, these two data structures, these two representations, and they would be good enough. And it depends on the application. So for example, if you think of very dense graphs that have, something like order n squared, theta of n squared many edges, then, working with the matrix representation is good enough. We are sort of not paying much more than we need to. If we're working with very sparse graph, let's say that we have, I don't know, 1 billion vertices, but only 10 billion edges. Let's say, think of like the graph of the internet, and we have like links between any two web pages if they link to one another. Then, you don't want to take 1 billion squared many entries to represent the matrix, right? It's too big. So for sparse graphs, we would pick the adjacency list. Okay, so this was sort of like a recap. We will talk today, we will think of the adjacency list model, okay? Any questions about that? This was supposed to be familiar to you?
I think some people are interested in using an adjacency set instead of a list. And are asking about that.
Right. So you're saying like to represent the list as using a set, using a hash table or something like that. Yeah. So that seems to work as well, but I don't think that we will need it for any of the applications that we will see today. Yeah. And this would, the main advantage is that you can do the check operation quicker, right? Because if you have a set, then you can access it in order 1. All right, yeah, very good question. Thank you. All right, so let's move on. So what we're going to explore in the next, couple of lectures is connectivity in graphs. And maybe the motivating example is, from childhood games. You have this. A lot of time in my childhood I spent on solving these mazes, right? You want to know if you can go how can you go from one side of the maze, from H to I, right? And you need to sort of try and maybe backtrack and then try again. So let's say that you are in this maze. Think of now that this maze is in 3D. And how would you navigate this maze? So we will see 2 algorithms how to navigate this maze and to find the exit. The first one that we will consider today is DFS, and the second one, which we'll consider on Thursday, is BFS. What are these acronyms? DFS is acronym for depth first search, and BFS is for breadth first search. Let's try to use the poll. So in the participants, you can say yes or no. So how many of you seen both BFS and DFS previously? Answer yes or no. Ooh. Okay, so you know this stuff. Okay, very good. So as I said, we will revisit these algorithms, and we will look at them in a more rigorous fashion, and we will prove why they work. Okay. So let's come back to the algorithm. How do you explore a maze? Well, one way that you can do it is, if you have like if you have a string and if you have chalk, right? So this is from the book. So what do? You just go you go always forward, and the string is attached to the starting point. So let's say to H, and you go until you cannot go further. When you cannot go further, you go back. Okay, so this is how you use the string. How do you use the chalk? With the chalk, you mark every place that you've been so far. So why are you using the chalk? The reason is that you don't want to sort of go in circles, right? So you use the chalk to not go in circles. So if you notice that you already visited a place, you sort of backtrack. Okay. So this is a guaranteed way to go in, from H to all the possible places that you can reach from H. And this is what we will prove. And let's formalize this as an algorithm. Okay, so how will the algorithm look like? Well, first I want to write the pseudocode of the algorithm Explorer. So we would have an array of everything that we visited so far. For every vertex, we'll have a Boolean flag saying, did we visit this vertex so far or not? And initially everything will be initialized to false. Okay. Okay, so now let's say that I want to explore the graph starting from the vertex V. So the first thing that I do is I mark it with my chalk, right? I say, this vertex is visited. And then the next thing that I do, and notice that I leave a gap here because I want to modify this algorithm later. So the next thing that I do is I go over all possible neighbors of V. And I check if the neighbor was not visited, then I recurse and I explore this vertex. Okay, so that's the explore algorithm. And the claim is that if I start explore, let's say from H, then I would, visit all the possible vertices that I can reach from H. So I would visit G, D, A, C, F, B, E, J, and I. So meaning all these vertices. I will not visit K and L because there's no way to go from H to K or to L. Okay, so this way I'm sort of exploring, everything that I can reach from a certain vertex, let's say from H. But if I want to sort of run DFS properly, I'm doing it not only once, but I'm doing it until I visited all possible vertices in the graph. So once I'm done with this component of H, I'm going to the next component. Let's say I start from K and I explore this component. Okay, so how do I do it in pseudocode? So DFS, I'm first initializing, my array of visited flags. So all the visited flags are marked as false. And then I iterate over all possible vertices. If they were not visited, then I explore them. Right? So what does this algorithm do? Right. So, right. And for that, for this algorithm, we talked a little bit about representation. Let's just think of the representation as edge list. Adjacency list. Right. So everything here would be very efficient if we think of this representation, because in particular, when we iterate here over all possible vertices or over all possible neighbors of V, we sort of, just read this list. So we don't need to do anything too complicated. Okay. So what does this algorithm, let's say that I run DFS on the graph G. What would be the final result? So I didn't return anything, notice, right? So the only thing that I did is mark vertices as visited. So what would happen is that I would mark eventually all vertices as visited. So it's a very weird algorithm. Why would I do that? Right? I can, if I just wanted to take an array and fill it with 2 flags, and I don't need to go over a graph, right? Okay, so the point is that this is sort of like a framework, and we will, you know, change it a little bit, and we will add, you know, steps before this iteration and after. So this would call the pre-computation. This would be called the post-computation, and we will show that you can do very sophisticated things if you do that. Okay. So any questions so far? All right.
We have why use a list and not a hash set, and why list and matrix are good enough for this class might be something to touch on.
Yeah, so as I said, for this algorithm to work, you know, efficiently, we would not benefit from having set versus a list, right? We are just going over the entire list. So there's no reason for this complication. So that, but you know, in some sense, you can just say that we abstract it away. So let's say if you want to replace your representation of graph with a set, you know, the algorithm would work just as well. Just the question is, you know, how do we implement this for all things, right? So then you would implement it by iterating over all possible keys in a set, right? Over all possible elements in a set, and not just by iterating a list. Yeah, so it's sort of a matter of choice, I guess. Just a little bit easier. Okay. So now we get to maybe the first you know, rigorous point. I want to prove that explore, when I run explore on the graph G, starting from the vertex V, then I visit all nodes that are reachable from V. So for example, if I'm looking at this maze and I run explore starting from H, I claim that after the explore on the graph and H finished, I sort of revealed and I visited this entire component, you know, this component. Okay, so why is this true? So when we have graphs, usually we will be, in particular when we're talking about connectivity, so we will prove things by contradiction, right? And we're going to use very strongly the fact that, you know, for a violation of this claim, so for a graph, if we have a graph G and a vertex V that violate this claim, what would we have? We will have some vertex U that is reachable in the graph, meaning that you can find a path from V to U in the graph, but you didn't find it using the runtime of the algorithm. But you didn't visit it. You didn't visit U during the execution of explore GV. So let's assume that. So what do we have? So we have V and we have U, and we know by assumption, we know that there's a path from V to U. So there's a path, and you know, we start from V, so V is visited. We assume that U is not visited. So there must be a point in this path where I have this situation where I have a node A and a node B, where A is visited and B is not visited, right? Sort of maybe I'm looking at like the last vertex along the path which was visited. It's definitely not the entire path is visited because we assume that U is not visited. So there must exist such a vertex, and the next vertex is not visited by definition. Okay, so why is this a contradiction? So notice that this path is not necessarily the path that I'm going to pick when I'm doing the, the DFS. Maybe in the DFS, I'm doing like a different path. Right? So I can do like this path. I don't know. Maybe I'm taking another path. The fact that the path exists doesn't mean that necessarily I'm going to take this path in the DFS. Okay, but what do we know? We know that at some point in time, we reach the node A. And when we reach the node A, B was not visited, right? And then we consider the edge AB. We considered it. And what did we do? When we consider an edge from a vertex A to a vertex B that is not visited, what should we do? We should explore B, right? So, but if we would have explored B, then B would be visited. So this is a contradiction. This cannot happen. Right? So of course I didn't write in words everything, but I gave a convincing argument why this claim is correct. And you can fill up the details if you write it down. All right, so I think this is a good point to stop for questions. Any questions? All right, very good. So I'm happy that it's clear. It shouldn't be too complicated, but things will get more sophisticated soon enough. So the next thing that I want to talk about is the DFS search tree. So when we explore a graph, we can write a tree that represents which edges we went through when we did this exploration. So let's see it by example. So let's say that we explore this graph and we start from A. Okay, so I'm at A and I need to pick a neighbor of A, so I go to B. I need to pick a neighbor of B, so I go to F. I need to pick a neighbor of F, so I go to C. Right? And now I'm looking at C, which are the neighbors of C? Only A, right? So I am considering this edge, but A was already visited, so I'm not going back. I don't want to go in circles. So this edge is not an edge that I'm taking, it's an edge that I'm looking at. So I'm like, C is looking, checking whether A is visited, realizes A is visited and not taking this route. Okay, so now we are done with C. So we backtrack because we explored all the neighbors of C. We explored all the neighbors of F, so we backtrack. We explored now we reach to B. B as a neighbor, E, right? And E as a neighbor, I, and I as a neighbor, J. Yeah. By the way, the fact that I'm doing these arrows is a little bit confusing because this graph is undirected. So let's not do the arrows. All right. Now I reach to J and I notice that J is not only connected to I, it's also connected to E. So I'm like, but I'm looking on E. E was already visited, so I don't need to explore it anymore. So now I backtrack. Okay, and I continue this way, and this is the graph that I get in the end, right? So when I do the DFS starting from A, this is sort of the structure that I see along the algorithm, where these, the edges, the thick edges are the edges where I actually made an action, meaning that I went, let's say here, this edge between A and B meant that, I explored A, and when I did that, I chose to explore B. And these dotted edges represent edges that I looked at, for example, this C to A, but I noticed that A was visited already, so I didn't go through this edge. Okay, and notice that when I drew this this tree with these extra edges, this is actually the same. This gives me the same representation of the graph. So I have every edge that appeared in the graph also appears down here. Some of them are thick edges, and some of them are dotted edges. And the thick edges form a tree, and that's a claim that is not too complicated to show, and so I will skip that. Okay, so when I do DFS, I'm actually not, I'm not finished when I explode A, because I still have K and L on the side. So then I explore K and I get this thing. Okay, so this is the DFS search tree. The edges of the tree are the thick edges, and the dotted edges are called back edges. So why are they called back edges? Notice that, if we think of it as a rooted tree, all these back edges go from some vertex to an ancestor of it. For example, C is a back edge to A, and A is indeed like the father of the grandfather of C. So a question about undirected graphs. Could it be that we would have an edge like this? Could it be that in the DFS tree we would have the edge like this, that it's not going from a vertex to its ancestor, it's going to some cousin or brother? What do you think? So some of you say yes, and some of you are saying no. So maybe someone wants to unmute yourself and give reasoning. So maybe I would say that the answer is no. So someone wants to justify why it's not possible.
Are we just allowed to jump in?
Yes.
Yeah, so my understanding behind why it's no is because if D were to have an undirected edge to A, that would mean A is also connected to D, which means we would have already drawn that line, and then we wouldn't have to we wouldn't have a back edge because we would have drawn it going forward.
Okay, so let's call this edge, this is not a back edge, this is a cross edge, let's call it. So the reason that, okay, very good, you explained it very well. Let me just repeat what you were saying. So why this cannot happen, right? So let's assume that we had an edge between E and D. So on the running time of this algorithm, E was explored before D, right? So at some point in time we reached, right? So let's say that at some point in time we reached E and we sort of explored this structure, but now we are not done with E yet, right? Because E still has an edge to D. So since we are not done with exploring all the neighbors of E, we would have to have D here, right? So I'm sort of assuming that there is also an edge between E and D. And therefore, if we would have a cross edge, then this would mean that we would reach a contradiction, because this means that, when we explored E, we didn't reveal D where we should have revealed D, right? The running, the definition of the algorithm says that we should have revealed D. Okay, so maybe this was a little bit confusing, but we will see the existence of cross edges when we talk about directed graphs. So I just want to point out that in undirected graphs, this is just impossible. All right, so let's erase this edge. All right, so now we move to the first interesting things that we're going to do with DFS. So it's kind of apparent from what we did earlier, right? So when we drew this search tree, that we actually figure out which are the connected components of the graph, right? So if we look at this graph, we sort of, when we drew these trees, we drew one tree starting from A and another tree starting from K. right? Each of these trees is called a connected component. What is a connected component? We say that two vertices U and V are connected if there's a path in the graph G from U to V. So maybe you have U going to A, going to B, going to C, going to V, maybe something like that. Now, this relation is an equivalence relation. Why is that? Well, it's reflexive. There's a path from U to itself. It's the empty path. If there's a path from U to V in an undirected graph, there's also a path from V to U. And it's also transitive. If there's a path from U to V and a path from V to W, there's a path from U to W. So if U and V, then also U and W are connected. So all these free properties says that this is an equivalence relationship. What are other equivalence relationship? We can say that two numbers are equivalent if their difference is divisible by 5. Right? This is another equivalence relationship. Okay, so what do we know about the equivalence relationship? We know that they partition the set of vertices into equivalence classes, right? And what are these equivalence classes? These are exactly, the connected components. In each of these subgraphs, we have a subgraph such that we have a path from every vertex in the subgraph to every other vertex. So these subgraphs are connected, but we have no edges between the subgraphs. Okay, so this is, for example, you can take a graph and look at its connected component. Earlier, these are the two connected components, 1 and 2. Okay, so how can we modify DFS so that it would tell us how the connected components occur in this graph, right? So we want, for example, that it would give us, for every vertex, a name of a component, such that two vertices are in the same component if they have the same number. Okay, so I will take DFS now and I will modify it only slightly, and we will show that this is in fact works. Okay, so what do I need to do? So the first thing that I do is I initialize a global counter that I call connected components. I initialize it to 1. And now, right? So, and now whenever I'm exploring, sorry about that. The component of V would be just this global counter. And when I'm done exploring a certain subgraph, I'm increasing the counter by 1. Okay, so that's the entire modification that I'm doing to DFS. And now what would happen? Right, so these are all the modifications that I'm doing. Now, what would happen when I finished running this algorithm? Not only I marked which vertices are visited, I marked for every vertex in which connected component it belongs. So in particular, if I run it, for example, on this previous graph, then all these vertices would be marked with 1. When I'm done exploring, I'm increasing the counter, and then I'm running it again on K, and now I'm marking all these vertices in 2. So you can see that, DFS is not a stupid algorithm. When we looked at it at first, it just marked all vertices, so it's not doing anything interesting. But if we modify it a little bit, we can already do something interesting. For example, figuring out which are the connected components in an undirected graph. Now, we will also see how to do it in directed graphs, but for that we will also need to understand what is the right equivalent, what is the right analog notion of a connected component. I think we will reach it only on first day, but we will show, we will sort of lay out the land today. And we will see most of the ingredients that go into the proof. Okay, so before we go into more application, I want to analyze the running time of DFS. So, so far we talked about divide and conquer, and we have these recurrence relations. Here, we will not, analyze the running time by recurrence relations. It's not like we have the T of n is, I don't know, 2 times T of n over 2. I mean, we will not have something like that. But what I want you to notice that when we analyze this algorithm is the following. How many times am I gonna, call the procedure or the subroutine explore on a given vertex V? How many times? I will do it only once, right? So every vertex I'm gonna, call explore with this vertex exactly one time. And for every edge in the graph, I'm gonna consider it exactly once if we are in the directed case, and exactly twice if we are in the undirected case. And when are we going to consider it? When I'm going over all possible neighbors of a vertex, right? I'm actually looking at all possible edges, and I'm doing it only once. So this type of reasoning tells us actually that the amount of operations that we are doing is constant per vertex and constant per edge. So overall, the running time of this algorithm would be order n plus m. And if you think about it, just to represent the input, we need to write down the vertices and the edges. So we need, so n plus m is sort of like the minimal amount that we need only to read the input. So DFS is really running in the best times that it could run. So it's a linear time algorithm in the length of the input. Okay. And of course, we modified DFS to do the connected components. We didn't do, right? We didn't change the running time. We just added like, order 1 operation per every operation we already did. Right. You should have noticed that I forgot something. I forgot to initialize the component. So, I mean, maybe it's not that important, but just to be on the safe side, when I started the algorithm, I initialized all the component to be null. Right. All right. So any questions so far? Okay, so now we move to the slightly more sophisticated and interesting case. What happens when we do DFS on directed graphs, right? So on undirected graph, we saw that, the DFS reveals us this search tree, and every connected component has its own tree. So it's actually a search forest, and we can get the connected components in the undirected case. What about the directed case? Well, we will see the algorithm next time, but notice that even to define connectivity, it's not as simple as that. For example, there's like a path from B to F, but there's no path from F to B. So are B and F connected? Well, according to the definitions that we will talk about later, which is called strongly connected, these are not strongly connected. We would demand that 2 vertices are strongly connected if there's a path from one to the other and from the other to the first one. Okay, so in both directions. Okay, so the main goal will be to figure out what are the strongly connected components in a directed graph. But before we do that, I want to look again at DFS in directed graphs, and I want to add two modifications to it. So I want to add for every vertex two numbers or times, the pre-time and the post-time, okay? I initialize all these pre-time and post-time to be null, and I have a clock that is initialized to 1. And whenever I start exploring a vertex, I, write down that the pre-time of this vertex was the current clock, and I increase the clock by 1. And whenever I'm done processing a vertex, I'm writing that the post time or post number of it is the current clock, and I increase the clock again. Okay, so then the point is that these pre and post numbers would be very, would reveal a lot of information about the structure of the DFS tree. Okay, and about the structure of the graph. So let's just run an example. So let's see how the DFS from A would look like on this graph, right? And I'm going to keep track of the pre and post numbers. Okay, so I'm starting from A. The clock is at 1, so the pre number is 1. So I'm writing for every vertex the pre number and the post number of this vertex. Now I'm exploring. I'm going from A to B. So the pre number of B would be 2. Now I'm going from B to D. From D to E. And now I have an edge from E to B as well, but I already explored B, so I'm not going through this edge. So this is a back edge again. So, okay, so after looking at this back edge, I noticed that there's no more outgoing edges from E, so meaning that I can, backtrack. So I finished processing E. I noticed that there are no outgoing edges from D that I've not explored, so I can finish D. I cannot finish B because there's still an edge to F. So now I'm going to F with the clock of 7. F is, a sink. There's no outgoing edges from F, so I'm backtracking again. Now I notice that A still has an unexplored neighbor, which is C. And C has an edge to E. But E was already explored, so we are not going on this edge. And then we backtrack and backtrack again. Okay. So this would be the pre and post numbers of all these vertices. And now I want to ask some questions about these pre and post numbers. Okay, so if you think about it, what do they represent? They represent the first time that the vertex was on the stack and the last time that it was on the stack, right? So when we are actually running this algorithm, whenever we call explore, we put something on the stack. And whenever we are done with the subroutine explore, we are actually popping something from the stack. So these numbers really represent the first time that a number was on the stack and the last time that the vertex was on the stack. Okay, any questions about these pre and post numbers? Okay, so I want to ask a few questions about that. So I want to look at all the possible edges in the graph. Okay, so let's say that I have some edge UV in the graph. And I want to look, at the starting point of U and the end point of U, and the starting point of V and the end point of V. Okay. So, okay, so the first question is, can I have that, that these are the numbers that U is put on the stack, then V is put on the stack, then U is popped from the stack, then V is popped from the stack. Can this be possible? Right, so everyone says no, and the reason is that this is simply not how stacks work, right? Stacks, how do they work? They work that, the first one to enter is the last one to leave, right? So for U to leave, we have to have V leave before it. So if this happens, then we must have that V is like that. Okay, so this is one type of relation between an edge, and this would correspond to tree edges, meaning these thick edges that we see along the DFS tree, and also to forward edges. Forward edges are something that we haven't seen in the undirected case, but they appear actually in the directed case. So let's look at this for 1 second. So let's say, it's actually here. Right, so yeah, I forgot an edge. So there's an edge here from A to E, right? But I actually have not explored it because by the time my subroutine on B finished, I actually explored E. So then when when A considers the edge AE, it didn't follow this edge. So in the directed case, we could have a situation like this, but notice that, the interval 112 contains the interval 4, 5. So we have the same relation in tree edges and forward edges. Okay, so we already said that this is impossible. What about this? Is this possible? Is it possible that we, explore U, finish exploring U, and then explore V, and then finish exploring V? Could this be possible? And notice that U and V is an edge in the graph. Okay. So I see, no, it's impossible, but all of you are saying yes. So, okay, so again, I'm asking the question. There's an edge UV in the graph, and then I start exploring U. I finish exploring U, then I start exploring V, and I finish exploring V. Is this possible? The answer is no. And why is that? Recall we had this claim, when we start exploring U, whenever we finish, we explore everything that is reachable from U. In particular, we explored V, right? So when we are here, we are considering the edge UV, and V is not explored yet, so we have to go there. So we have to put it on stack. So this is still not possible. I think that there's another reason why you were confused, and the answer is that when I swap the orders, then this is possible. So this, on the other hand, is possible. And recall that the graph is directed now. So the reason that this is possible is that the fact that we have an edge from U to V doesn't say that we have an edge from V to U. Maybe the entire graph is just U going to V, right? So if we explored V first, we have nowhere to go, so we finish. And then we explore U, and then we consider this edge. So if we do DFS on this graph and we start from V, the structure that we'll see is first V, and then we're gonna see U with a cross edge to V. Okay. So this is called the cross edge because it's not an edge in the graph, in the tree, and it's also not an edge going to an ancestor or a descendant. Okay, and the last one is the possibility, which is similar to the tree edge, but it's backwards. And this would be a back edge. Okay, so now I just want to look again on this thing, on this example. So this would be a cross edge, right? Because it goes from C to E. C and E are not, ancestor of one another. This edge from A to E is a forward edge. And this edge from E to B is a back edge. Okay, and all these relations can be figured out just by the pre and post numbers. Okay, so, all right. So now I want to show you why are these numbers very useful. So we're gonna go over an example of topological sort. Yeah, if you have questions, by the way, it's a good time to ask. So maybe there are some questions about this. Yeah.
I was just going to say that there are a bunch of questions coming up about how pre and post numbers and this bracket notation applies to directed versus undirected graphs.
Right. So you can also think about these pre and post numbers in the undirected case. There are more impossible relations. So we only have tree edges and sort of back edges. I mean, it's hard to say if an edge is back or forward in an undirected graph, but right. So these cross edges we said before are impossible if the graph was, if G is undirected.
There's also a question about back edges and saying that Doshi still need to open U first in a back edge, sorry, in a cross edge from U to V.
Can you say it again?
There's a question that if there's a cross edge from U to V, do you need to still open U first to get to V?
So a cross edge from U to V is sort of an edge that does not appear in the DFS forest. So for that, I have to have V explored before U, because if U was explored before V, then I would actually go on this edge, right? Recall that when I'm running explore on U, I'm checking all the neighbors of U. If they were not explored, then I'm going and exploring them. So in this situation, if, when I already explored V and now I'm looking at U, then I'm not going to go to V. But if I would have considered it in the other way around, right? So meaning that, so it's a little bit interesting. It seems that the tree actually depends on the order in which I picked elements. Okay, so that's interesting, and it's sort of something that we haven't seen in the, right? We haven't seen it in the case of undirected graphs. In the case of undirected graphs, it seems that at least, here, this is sort of the DFS forest. It's just two isolated vertices with a cross edge. But if we would have started from U, then we would have this tree. So we would have gotten something quite different. So it seems that it's a little bit more difficult to understand the structure of connected components in directed graphs, because it sort of seems to depend on the order on which we're doing things. Okay, and we will get to it soon. Okay, so now I want to go to another application. So this is some task that maybe might be relevant to you. So let's, I went a few weeks ago to a very fancy restaurant, and I needed to figure out, how to dress up. Okay, and there are some things that you have to do before you do other things. You have to put your socks before you put on your shoes. And some people say that you have to put your pants before you put on your socks, because otherwise it looks weird. Okay, so let's say that you have this graph of all possible, clothing items, and you have an edge, directed edge between two of them, if you have to put one before the other. Okay. All right, and now the question is, can you find an, in the end you want to get dressed, so can you find an order that satisfy all these edges? Meaning, can you write, you know, on a line all these vertices, let's say. So okay, so on and so forth. So can you write them on a line so that all the edges go forward, right? Meaning that whenever you are getting dressed, you sort of, you have all the closing items that you already need before making the next step, right? So this is the question. And in this case, you can do it. You can, it's not too difficult to show, but in general, the question is, how do you do it algorithmically? Let's say that I give you a graph. Can you find an order, you know, a linear order, such that all edges go from left to right? So that's a question about graphs. So this is relevant, you know, only if the graph is directed. And so there's actually two questions. One is there an order like that? So maybe some graphs don't have an order. Maybe the graph looks like this. A must happen before B, B must happen before C, and C must happen before A. Sometimes you hear these, you know, cyclic constraints, and you realize, well, I cannot satisfy these constraints, right? Because something has to happen first, and nothing can start happening. So this cycle means that there's no topological sort in this graph. So the type of graphs on which there exists topological sort is what called directed acyclic graphs. What are directed acyclic graph, or DAGs? These are directed graphs that have no cycles. Okay, so this is just a definition. A directed acyclic graph is a directed graph with no cycles. And now the claim is that if we have a digraph, we can check if it's a directed acyclic graph. How can we check it? If and only if in the DFS tree, there are no back edges. Okay, so I claim that there's a cycle in the graph, in the directed graph, if and only if there's a back edge somewhere along the running time of DFS. So back is not the same as cross. Back is really back. Back is sort of, you know, right? It's a back edge here is from E to B, right? So we went from B using, you know, we explored from B, D, and from D, E, and then we had considered the back edge from E to B. So this indicates that there's a cycle. Okay, and I claim that this is an if and only if. So cross edge is not an indication actually of a cycle. If you have cross edges, only cross edges, then you don't have a cycle. Okay, so how do we prove that? So there are two directions, right? It's an if and only if. So if there's a back edge, that's easy, right? What does it mean that we have a back edge? It means that, you know, we started exploring U first, and then after exploring a few vertices, we reached V, and then we considered this back edge. So if we just consider the path from U to V along the search tree, the DFS tree, and the back edge, this corresponds to a cycle in the original graph. Okay, so that's easy. Let's see the other direction. So let's assume that the original graph G contains a cycle. So there's some vertices that sits on cycle. So let's say V1 points to V2, that points to V3, up to VT, and VT points to V1. Now I claim that I will find this cycle no matter in which vertex I'm starting the DFS. Okay, so let's show why this works. So consider the run of DFS on the graph containing this cycle. Okay, there would be a first time in the running time of the algorithm where one of these vertices is explored. Maybe the first vertex that is explored is V3. Okay. Now notice that since we can change names of the cycles, it's sort of the same as if we think that the first vertex is V1 or the first vertex is V2, because we can just write the cycle, we can just write it like this. So just to keep things simple, let's assume without loss of generality, let's assume that V1 is the first vertex that is explored in the DFS. Now notice the DFS doesn't necessarily follow this path. It may go in other paths, right? So it sort of creates a tree. So it's not necessarily that all possible edges in the original graph would appear as 3 edges. Nevertheless, there would be a certain point in time where the first vertex in this path would be explored, right? So let's assume that it's V1. Now, what did we prove about DFS? We proved that if we start exploring from V1, then by the time we finished, we have explored all the possible vertices that are reachable from V1. Right? Recall that this is what we proved earlier. So we know that by the time we finish exploring V1, we must explore VT. Okay? In other words, it means that V1 has some grandchild. We have VT. Maybe not according to this path, maybe according to a different path, but we have to go to VT at some point. Now we reached VT, and there's an edge from VT to V1. This edge is a back edge because V1 is an ancestor of VT. Okay, so this is the proof. I mean, there's obviously some text that you need to add to. I mean, if you just write these 3 lines without explaining it in words, it's a little bit hard to parse. But this is more or less the proof. Okay, so great. So what does it mean? It means that if we run DFS, it's very easy to know if we have back edges. So DFS itself detects if a graph is a digraph, is a directed acyclic graph or not. And now I want to say something more. Not only it detects that, it also finds a topological sort. And where we show that, we will actually show that every directed acyclic graph has a topological sort, which was not obvious to begin with. So here it's kind of magical. We are proving that an algorithm works, but we are actually proving something about the structure of the graph. We're proving that every directed acyclic graph has a topological sort. How? By running an algorithm on it and claiming that the algorithm runs correctly. Okay. So the claim is that if we have a directed acyclic graph, and we have some, edge UV in the graph, then the post number of U would be bigger than the post number of V. Okay, why is that? Well, right, so we consider all these possible scenarios, right? UV is an edge. It could be that, UV is Right. Let's see. So it could be that if UV is an edge, it could be that you know, it's an edge on the tree, or it could be, you know, a cross edge, or it could be a back edge or a forward edge. So we just need to check all these options. Okay, so if it's a cross edge, it means that we already finished processing V. So in this case, definitely the post number of U is bigger than the post number of V. So let's look at the. So if it's a tree edge, also we have the following, right? So if there's an edge from U to V, then the post number of U is bigger than the post number of V. And the only problematic point is a back edge, right? Here, the post number of U is smaller than the post number of V. But what do we know? We know that in a directed acyclic graph, we have no back edges. So this is impossible, right? Yeah, sorry, I was a little bit confused because the back edges confuse me, but we have no back edges, right? So that's the things that we need to assume. So this is, you know, just by, you know, we check all cases. So it's true for forward edges. It's true for cross edges. And it's true for tree edges. And it's false for back edges, but in a DAG, we have no back edges. So that's okay. So what does it mean? How do we get a topological sort just by this claim? What will be the topological sort? What will be the order? Yeah, so. Right, so it will be just the decreasing order of the post numbers, right? If we order them according to the post numbers, we know that all the edges would go from, you know, if we order them by post numbers, so here we would have like post, I don't know, 12, post 11, and so on. Then, and here we have UV. So we know that all the edges will go this way, would go from vertices with higher post numbers to vertices with smaller post numbers. So the post numbers really give us the topological order. I mean, up to reversing it. And next time we're going to see how these post numbers allow us to find the strongly connected component in a graph. Okay, so we have a few minutes left, and I'm happy to take questions.
So just real quick, wondering why we can't look at decreasing pre-visited numbers?
Why can't we look at decreasing pre-numbers? So there's like a counter example. Let's see if I can see it. Okay, so let's look at that.
I meant to say increasing.
Yeah, sure. I figured it out. So what if we have this thing? Okay, so the pre-number, so let's say that we explore this graph. So we start by A, so the pre-number is 1. Then we go to B, pre-number is 2. Then we finish. Then we go to C, the pre-number is 4. And then we have this edge, right? So what would be the order? According to the pre-numbers, we have A, B, C. But notice that we have this edge. So it doesn't work. So here's a short counterexample. But I guess we can also look at the cases and notice that the problematic thing is probably the cross edge. The cross edge would sort of violate that. Right. So what do we have in a cross edge? In a cross edge, we have that UV is an edge, but U starts later than V. So we can see that here the pre-number of U is later than the pre-number of V, but the edge goes from U to V. So a cross edge violates this suggestion. Is it clear? I hope it's clear. Okay, so maybe let me do an advertisement for what's going to happen in the next meeting. So in the next meeting, we're going to look at two algorithms. So the first algorithm is called strongly connected component. So we will define a relation in a graph. I already defined it, I guess, in words. So we say that two vertices U and V are related if there's a path from U to V, and also a path from V to U. So this is really right what we think of when we say connected in a directed network. Let's say we have a network of roads. What does it mean that my house is connected with Soda Hall? It means that I really want to go from one place to another and back, right? So I'm not satisfied with only going one direction. This would be very miserable. So what we want to identify, in a directed graph all the strongly connected components, and we will see that a very sophisticated but very small adaptation of DFS gives us this information. So it tells us for every two vertices whether there's a path between them or not. Sort of similar to how we had the connected components, we would sort of color every component in a different color. So this would be in the beginning of next time, and then we'll start talking about distances in graphs, and we would recall the BFS algorithm, which almost all of you have seen already, but we will show why it works, and then we will discuss further the extras algorithm, prove that it works, and we will later talk about what to do in the absence, when we have negative edges. So this is what we're going to have in the next meeting and even the meeting after that. And yeah, feel free to stay on the line and ask questions, clarification questions, and yeah, thanks.
Professor?
I have a quick question.
Maybe you can raise your hand just so that we would have an orderly queue.
Okay, Luke first because he's raising his hand.
Yeah, my question is, can you clarify what the cross edges are?
Right. So what is a cross edge? A cross edge occurs when I am sort of exploring some vertex, and I finish exploring, all its descendant on the left, let's say, and then I start exploring on the right. But then I notice that there's an edge from the right child to the left child. So this is a cross edge. I'm not going to go over this edge. But it's also not an edge between a vertex and an ancestor in the DFS tree.
Okay, so just like in the earlier example that you used, so like going from U to V, but if we explore V first, so we can like close V and then explore U. So in that case, what did you mean by like the cross edge?
Okay, so in the cross edge, right? So just to be on the same notation, so let's say this is the cross edge UV, and let's call this W. Okay, so then I wanted to identify cross edges from the pre and post numbers. So when I'm exploring the tree like that, the pre and post numbers would look like this. So we're first going to explore V. I mean, I'm only considering V and U, so there are a lot of other nodes in the graph, but we are going to start exploring V. And then we're going to finish exploring V, right? Backtrack, go back to W. Then we go to W, from W to U. Then we're going to start exploring U. And in the end, we're going to finish exploring U. So this is how a cross edge looks like with the pre and post numbers. Okay, so you see that the intervals are disjoint. The edge goes from U to V, and the interval of U comes later than the interval of V. Okay, so this happens because we sort of explored V. We reached everything that we could have reached from V. We could not reach from V to U, right? This is not the case, but we can reach, but we have an edge from U to V, right? So this is a cross edge.
We also have a question from Jason, and then after that, Clara.
Okay.
Yeah, I have a question. So you can label the post numbers in with depth first search in O of n plus m, and then I guess to get the topological sort, you sort like in O of n log n. Is there a faster way to do this, or like is there a faster way to get the topological sort?
Interesting question. Well, one thing that you can say is that you are sorting numbers that are in the range 1 to n. So you could do like, right? So if you know that you're sorting numbers in this range, you can do it in order n time with random access.
Yeah, that's fair.
Right?
Okay.
That's one thing. And probably you can also do it, more directly, but I'm blanking.
Oh, if you just append to a list, like instead of setting a post number, if you append it to a list,
right?
Would that do it in O of n plus m?
Right, exactly, correct. So instead of just recording the post numbers, what if whenever you're, finishing processing a vertex, you just, push it to a list, right? So then this list would be sorted according to post numbers.
Awesome, thank you.
So yeah, very good. Yeah, okay, thanks for helping me.
Yes, I think I was next. Would you mind also walking through an example like you did with the cross edge, but for a back edge?
Right.
Thank you.
So how will a back edge look like? So in the tree, we know how it looks like, right? It looks like maybe we have here V, W, U, and then we have an edge from U to V. So that's a back edge in the tree, right? Maybe we have more things. So in the tree, it's an edge from a vertex to some ancestor of it. Maybe its father or the grandfather or the, more than that. How would it look like in terms of pre and post numbers? So let's look at this. So V is the grandfather. So when V starts first, then U starts, then U ends, and then V starts. So this is how the back edge would look like in terms of pre and post numbers. So V would be first on the stack, then U would be on the stack, then U would be popped from the stack, and then V would be popped from the stack. So this is a relation between the pre and post numbers and the back edge. It would look like that. And recall, we always think of an edge from U to V. Clara, does this answer your question?
I think so. I'm just, I think, a little confused with the case with the forward edge, where that would be U, V, V, U.
Right, so forward edge is similar, but so again, I'm changing the names now because I want to do a forward edge. So the forward edge would look like that, right? And so, right, so we could have a graph like that, right? U, W, V. When we start exploring U, we explore W first, and then when we explore W, we explore V, and then we explore everything, so we just backtrack. But there's still an edge from U to V. So in this case, the relation would look like this. First U is open, is pushed on the stack, then V. I mean, it's the same thing, but notice that, you know, U and V are changing roles. This is a forward edge. Right? So again, there's an edge from U to V. It's not an edge on the tree, but it's a edge that is doing some shortcut to a grand key. Right? So U sort of has a direct link to W, and W has a direct link to V, but U also has a direct link to V. So it's sort of like a shortcut, if you want, or a forward edge.
Okay, thank you.
We have Selena and Ian also.
I had a quick question about the definition of a source and a sink. It was in the textbook, and in the textbook, they say that the vertex with the highest post number is a sink, and the vertex with the highest, the smallest post number is a sink, and the vertex with the highest post number is a source. So I think what I was confused was I thought post numbers were supposed to be larger than pre-numbers, but I'm not quite sure if that's the right.
Okay, great question. I didn't mention the notion of sinks and source. Okay, so let's look at this example of the topological sort. Okay, so this graph is a directed acyclic graph, right? There's no cycle in this graph. And also there's a topological sort. And we actually showed that you know, if there's no cycles, then there's a topological sort. This is actually what we showed with running the algorithm. Okay, and it's an if and only if, because if there's a cycle, definitely there's no topological sort. Okay, but another way to see it is to consider, as you said, sinks and sources. So what is a sink? A sink is just a vertex such that there are no outgoing edges from it. Okay, so in this case, like a belt is a sink and a bow tie is a sink, and also a hat. So this is a sink. And we have also sources, right? So sources are ones that there are no incoming edges to them. So this is a source. So another way to solve topological sort is to sort of figure out which vertices are the sources. Now you can convince yourself that there must exist a source in a directed acyclic graph. Why? Because you can sort of, you know, start from a vertex and go backwards until you cannot go backwards anymore. And this would be the source. So I don't know, maybe you started here and then you go backwards until you cannot. So you go backwards, you get to this, and you see that this is a source. Okay, and the reason that you cannot get stuck is that there are no cycles. Okay, so another way to solve topological sort is to, you know, put, you know, to take the sources to be the first element, and then to remove them from the graph, and then to take the sources in the remaining graph as the next element, and so on and so forth. And this is another way to do topological sort, not using DFS. But notice that, right, so we said that DFS, the post numbers gives the topological order, right? What will be, in topological order, the first element must be a source, right? we cannot have any incoming edge to it. And the last element must be a sink, right? Which is maybe both. This have to be a sink, because if we have an outgoing edge from it, this will violate the topological sort. So just by the fact that, you know, our algorithm, the one that sort of gives the post numbers and sort according to the post numbers, gives the topological order, just by this fact, we know that the first element in this order is a source and the last is a sink, and this is exactly what you were saying. Does this answer your question?
So I guess so as we go through the sequence, would posts increase or decrease?
The post would decrease. So this would have like the highest post, and this would have the lowest post.
I see.
And what we claimed here is that this is actually a topological sort, right? That if we orders the vertices according to decreasing post numbers, and then this would be a topological sort.
Okay, that makes sense. Thank you.
All right.
So I had a question on, hold on, let me see, my microphone's on.
Yes, are you Ian?
Yeah,
Okay,
okay, cool. Yeah, so I had a question about the cross edge. So I was a little confused because both the pre and the post number for V would be greater than the post number for U. Wouldn't that mean that we visit U before V? So I was just confused why like we had the V before the U in the stack, like the stack diagram when describing the cross edge.
right. So I guess maybe what's confusing you is that this is a directed graph. So in a directed graph, we could visit V, and there's no way to go from V to U. Okay, so maybe V is a sink. So we visit V. V is a sink, so we finished visiting V, and then only afterwards we've started visiting U. Right, so this could have happened. Right, so this is maybe an example for that, like the same example as before. Right, so what if we are exploring this graph? So I claim that if we, you know, explore A and then go to B, then we are stuck. B has no outgoing edges. Then we have to backtrack, and then we have to go to C, and then we realize, oh, there's an edge from C to B. This would be the cross edge.
Oh, I see. I thought it was the other way around, like B points to C. So that's why I was confused.
Yeah, no, it's not going to be. So all the edges are edges of the original graph. We are not inventing new edges. We're just sort of noticing, you know, how does these edges look in the tree structure? Do they connect to an ancestor, to a descendant, or to someone else? In the case of someone else, we call it the cross edge.
Okay, cool. Thank you.
Yeah, just, I mean, if you are confused about this, just work out, like there's like one example in the book, like with, I don't know, 10 vertices, just run it, work out the pre and post numbers and see for yourself. I mean, I think this would be much more helpful than you know, just thinking of it abstractly. Just do it once and it will be very clear, I think.
Very cool.
Yeah.
I don't know if there are more questions, but I know someone asked if the slides that you were writing are going to be posted after the lecture.
Yeah, I can post them.
Okay.
Yeah.
I'll put that in the piazza.
Hi, Professor. I wanted to very quickly ask about the purpose for creating this sort of like pre and post timing of our graph traversals. I understand that it sort of like indirectly builds this picture that shows how deep you can go from a certain node, but I'm just like, I guess, tangentially curious about the potential applications for it.
Well, we already saw one application for it. We saw that using the post numbers, you can topologically sort vertices. So this gives you an algorithm just by these numbers. Next time we will see that these pre and post numbers are allowing you to compute the strongly connected components. So yeah, so it's not only a thought experiment. These are really useful things, and they are quite simple if you think about it. They just represent the time in which vertex was put on the stack and which this vertex was taken away from the stack. So, yeah. And
Okay,
it's sort of easy to argue about the tree once we have these numbers, right? So we can argue about these edges going forward, backwards, or across. Yeah. All right, if there are no more questions, I invite you to attend my office hours, which will be on Monday at 10:30. And you're also welcome to ask posts on Piazza, and we will be happy to clarify anything. Right. So see you next Thursday. This Thursday.
Okay, I will stop the recording now.